minds how item response theory or item response models could be reconceptualized as multi-level models. And so we've talked, if you've had multi-level classes, the kind of simple example is students nested within schools. It's individuals nested within groups. You can add additional levels onto that hierarchy, but you can also go down. We have time points nested within students, for example. So one thing that we did was reformulate it as items nested within students. So we conceptualized it as a multi-level model where the grouping factor is the student, and the repeated factor or the within cluster factor is the items. In other words, one student takes multiple items, so his or her responses are likely to be correlated above and beyond just random chance, and their correlation among the responses is in all likelihood due to the latent dimension that you're trying to test. So for example, if you're trying to test reading comprehension, you would suspect that a child's reading comprehension ability influences his or her response to all the items, such as item A, B, and C. So that excess correlation is due to the reading comprehension factor. So when we reconceptualized it, we talked about the difference between, or the similarity between random effects and latent variables. They're really the same thing. In multi-level models, we typically call them random effects. These are effects that are attributable to groups, such as how does a school impact a student, or what is the effect of a school on a student, or what is the proportion of variance in a student outcome that is attributable to differences among schools. When it comes to IRT, or item response theory, we typically call the random effect a latent variable. And this is an unmeasured or an unobserved variable that we believe exists, at least in theory, and we believe that that latent variable informs responses to different items. These are just different conceptualizations of the same idea. A random effect and a latent variable are synonymous. Once we framed item response theory as a multi-level model or a cross-classified model, it opened up a lot of different possibilities. We haven't really talked much before this about including person covariates or group covariates or item effects or item covariates. And so what we did in our past classes, once we reformulated IRT as a multi-level model, we started to talk about explanatory item response models, or just explanatory or conditional multi-level models. Just like in a regression model or in a multi-level model, you would include covariates to try to explain some of the variability. You can do the same thing when you reformulate item response theory as a multi-level model. You can include variables that represent item characteristics, such as whether some items are negatively worded. You can include variables that represent differences among individuals, so for example, background characteristics of an individual student. And you can make it a three-level model, even where you have items nested within students, students nested within schools, and you can then include school-level variables as well. So when we have students nested within schools, we usually talk about that as the kind of model, or the multi-level model, or the structural model. And then when we have items nested within students, we usually call that the measurement model. That's the part that focuses specifically on tracking an individual latent variable or a random effect. And we also talked about how this all dovetails into structural equation modeling. Explanatory item response theory is one way to reformulate item response theory as multi-level models, and to kind of use generalized linear mixed models and nonlinear mixed models to identify random effects or latent variables. But explanatory item response theory, or these multi-level models, are just also instances of structural equation models. So all of these things kind of intersect in different ways depending on how you formulate your statistical models. We also talked about the difference between random and fixed effects, and that's a little bit difficult to explain very succinctly when you haven't had something like multi-level models or linear mixed models class on that. But the kind of conceptual way that we tried to describe it was random effect models treat certain effects as if they were sampled, as if some of the levels of that factor were sampled from a larger universe that you're interested in generalizing to. So for example, you could treat schools as a random effect because you sampled, say, 50 or 100 schools out of a universe of 1,000 schools, or whatever your target of inference is, your population of inferences. And so we sampled, and and we want to generalize. We want to develop a model that generalizes not just to these schools that we sampled, but more largely to the entire population, to draw inferences at the population level. Random effects, the way that it kind of treats it in terms of estimation, random effects or latent variables are typically marginalized. When we're doing some type of estimation like maximum likelihood estimation, we usually do marginal maximum likelihood. In other words, we marginalize or we integrate out those random effects. We effectively treat them as an incidental or a nuisance parameter. So for example, when we're doing item response theory, what we've been doing in the background typically is using maximum likelihood to estimate the item parameters. And the problem that arises is a major difficulty and challenge in estimating a lot of the models that we're talking about is that they're nonlinear models. So to be clear, what a nonlinear model is, it means it's nonlinear in the parameters. So for example, in a simple situation, you have linear regression. You say yi equals beta 0 plus beta 1 times xi plus epsilon. This is a linear model, so you model things with a rough, you approximate them with a line. But linear models can also do things that are nonlinear, very simply. You could have, for example, yi equals beta 0 plus beta 1 times xi plus beta 2 times xi squared plus epsilon. So this involves some type of non-linear form. So it captures non-linearities between the response and the predictor. The key thing is, both of these equations are still linear in the parameters because the unknown parameters, namely the betas in this example, they all enter linearly. They're not multiplied by each other. This is not the case when it comes to at least 2-parameter item response models. And in 1-parameter model, the Roche model, it still is the case. But in our case, we've had, say, the log odds of probability that y equals 1 divided by 1 minus the probability that y equals 1 is equal to A, I, put, say, I, J, so this is J for items, theta times I minus B times J. In this instance, A is unknown, theta is unknown, and B is unknown. If you multiply this out, you get AJ times theta I minus AJ times BJ. Right here, and right here, this is a multiplication of unknown parameters. So it's no longer linear in the parameters. So now we have a non-linear model. Those are very difficult to estimate. So one of the ways that we've been doing that, well, so the question arises, how do we identify A, or how do we estimate A and B when we don't know theta? It's kind of akin to saying, how do we estimate beta 0 and beta 1 when X is unobserved? So the way that we've been doing that is through marginal maximum likelihood for the most of the semester. What we've been doing is treating this as an incidental or a nuisance parameter, and we integrate it out of the log likelihood and then estimate A and B. Having estimated those, then we can kind of use the maximum likelihood plugins for A and B to go back and then estimate theta. And there's this iterative process flipping back and forth between those. So random effects, in this case, we've been treating theta, just like a multi-level model would, treats theta as a random effect and A and B as fixed effect. In other words, the theta is, we're using it to make a generalization. We're treating it as a random effect because we're not just interested in these kids. Maybe you do have a strong interest in these kids, but we're not just interested in those kids. We're interested in how this test or how this assessment would perform among a larger population. And so theta is considered to be a random effect, in other words, a sample of individuals from a population. And those individuals are not of particular interest. Maybe they are, but for the moment, we're not going to treat them as particular interest. We're interested more in generalizing. However, A and B are typically treated as fixed effects because we are interested in the items that we have. We're not interested in generalizing to a larger pool of items. So we use a fixed effect in the sense that we actually estimate these directly. We don't integrate them out. So this can also be relaxed. Now, the difference between random and fixed effect, it seems in some ways very important, and it is very important, but it's typically not as critical as you might think. The reason why we typically treat theta here as a random effect is because if you were to treat it as a fixed effect, you actually get biased answers for the A and B parameters. In other words, simultaneous estimation of all these parameters, treating them as fixed, actually gives you the wrong answer. It gives you some biased answer. And so the problem is, we don't know A. In order to estimate A without bias, we need to know theta. In order to estimate theta without bias, we need to know A. But you don't know either one of them. So one of the improvements in the past 30 years was marginal maximum likelihood, a way to kind of treat this as a random effect and integrate it out and still get unbiased answers. So when you estimate all these simultaneously as a type of fixed effect, it's joint maximum likelihood. When we come to this multi-level formulation, we can develop a type of cross-classified structure as well. And so now we have items nested within students, but we can consider them to be cross-classified among students. Instead of item A, B, C being nested in student 1 and item A, B, C being nested in student 2, we now have them cross-classified. Put differently, we can now treat items and students as random effects. So we can now treat theta as random, A as random, and B as random. And so what that would suggest, at least conceptually, is that you're intending to, you're conceptually saying that the items that you have in your sample are a sample of items that are representative of a larger pool of items. And you're trying to draw inferences as to what is the general distribution of the difficulties and discrimination parameters for this larger pool of items. In some fields, this is very difficult to conceptualize. If you're talking about, for example, quality of teaching and rating teachers, you can have 4 or 5 indicators that take a long time to develop. It's very difficult to generate new indicators. In other fields, it's very simple. So if you're talking about addition, well, you have 2 plus 3, or 4 plus 7, or 9 plus 17. You have all these different problems that you can just generate. So you just happen to use a test. On a test, you happen to use 10 items. What is 7 plus 2? What is 4 plus 3? You have just samples of those. In that way, you can actually conceptualize the items as a sample of items from a larger population of items. In the end, whether you treat the item parameters as random or fixed has very little influence on your estimates. The one key is that as long as you have kind of enough items, if you only have 3 or 4 items in your sample, it's really difficult to treat them as random, because what you're doing with random effects is you're assuming that those 3 items are representative of all the items, or a good sample of all the items, and you're trying to estimate the variance among the items in terms of their difficulty and discrimination parameter. Well, that's really difficult to do with 3. Think about trying to estimate the variance with 3. Almost always it's going to be downwardly biased when you have a very small sample. This is not a problem specific to IRT, this is a larger problem. If you have a very small sample size, it's really difficult to get a good idea of the variance. And so you need something more like 10 items, or somewhere around, or maybe more, between maybe 7 to 20 or more, in order to be able to use kind of random effects for the item parameters as well. However, the larger idea here is that by reconceptualizing these models as multi-level models, and in this case, cross-classified models, it opens up a lot of possibilities. Before, we just functionally assumed that the item parameters were fixed. We did that, we didn't even know we were doing that. That was just kind of tradition or practice. Now, when we reformulate it, we realize all these different bells and whistles and all these different approaches that we can do. And so this is one of those nice utilities beyond covariates and things of that nature.
Ben, can I ask a question? If all of your parameters are freely estimated, does that
What is freely estimated?
Well, not freely estimated, are random.
Yeah.
Sorry, not fixed. Does that have any implications for identifying your model, or do you still, how do you
You still have to set the scale of the model using
Okay.
something.
Okay,
So you still, a loading or the variance.
okay.
But when you get, we'll see in an example in a minute, what you get out of it. So in our typical model, you remove all these extra circles here. In our typical model, we made the assumption that typically we say theta as a distribution that's approximately normal, centered at 0, and with a standard deviation of 1. Or you could fix a loading on one of these A parameters. Now, once we've done that, we can say AJ is normally distributed with a, what the mean is would be something like, let's just call it A bar, what the average average discrimination parameter is, with some variance, sigma squared sub A. And that describes the variation among the discrimination parameters, or the variation in the discrimination parameters among the items. And that, and then B sub J has a similar distribution, centered at the average B with variance B sigma squared B sub B. So what you get, we didn't make these assumptions before. We didn't make them. We just said theta was normal 0, 1. And then A and B were estimated as fixed effects. If you're willing to induce or draw on these assumptions, and you don't have to do that blindly, you can test these, right? If you're willing to do this, well, then all of a sudden you have your model gives you the ability to generalize to other items like these items. So in other words, what happened if we were just sampling items? So you're talking about maybe the GRE, right? What they do is they have a large bank of items, and they just sample items. Every person gets a different combination of items on these computer adaptive tests. And so now you can understand what is the variability in my item pool, right? Do I have, the difficulty one's a little bit easier to interpret, but do I have items that sufficiently span the continuum of abilities? Do I have items that are, all the way more in the difficult range and all the way more in the easy range? So by introducing these two assumptions, you can get more information. You can tend to generalize. In some ways, it also makes it a more parsimonious model, because before you were estimating an A and a B for every single item. So if you had 10 items, you would have 10 discrimination parameters, 10 difficulty parameters. Here, you only estimate one parameter. You're only estimating the variance in both of those things.
Yeah.
So the practical difference is usually very small. The nice thing so in some ways, it's just kind of like, oh, this is neat, this is nice. And it is, but the results that you get out at the end are not that different, provided that you have 10 or more items. If you have 5 items, you really can't use this because you can't estimate the variance very well. So in some ways, it just feels neat for a moment, but then when you start to unpack it a little bit more, or push into it more, what you find out is, oh, well, with these, when I do the cross-classified, where I treat the item parameters as random, I can actually do an explanatory model, because these are random effects, and I can get an idea of what the variance among the items is, but then I can also explain that variance using item properties. And you can't do that in the fixed effect model. And what I mean by that is we have covariates for individuals. You all know there's a bunch of different covariates. They're pre-test and all their background characteristics. You have the same type of things for schools. But people have not thought typically of item characteristics. These are features of the item and how they're worded and how they may make an item more difficult or more easy. Right? These are doing actual content analysis of the items. In other words, it's survey design, reading through the items and trying to understand, what are these items saying? What features do these items have that make them difficult or better discriminated? In my simple, ridiculous example was, if we're doing a bunch of addition problems, and then I say, what's 2 plus 3? I have all these single-digit questions, and then all of a sudden I have a triple-digit or a double-digit question. What's 104 plus 97? Well, that's a much more difficult question. And so one of the features that you might suspect that's common across items, or an item feature, is double-digit addition. And you might suspect that there's variation in the difficulties among items, and one feature that explains the differences in difficulty is single-digit versus double-digit. Now that's a very simplistic example, but there's much more sophisticated examples as to why certain items make them more challenging or make them more discriminating. And so it opens up this possibility that we can actually now do test design or survey design in empirical ways to assess the quality of our items or how they're actually functioning. And you can actually build a recipe or a formula to do, for example, computer adaptive testing. Right? You can actually say, well, this item, we don't know what the difficulty of this item is just yet, but we predict it to have a certain difficulty because it has these 5 features. Or it may be best discriminating for people of this certain background because it has certain features. And so there's a way to use these to explain how people are interacting with these items, or how the parameters of these items govern people's responses or influence their responses.
I see it like, oh, sorry, I didn't mean to. I see the practical applications, especially if you have assessment, like GRE or something, much less so for maybe more the type of research I do, which is Likert type 5 items.
Yeah.
I don't know a case when you would ever, like, how do you make a more difficult social norms question?
Well,
and you only
give
have
me an
5
example
items.
of a question, I guess. What is maybe?
Okay, so very specifically, so kids learn about hazard mapping, which is going into your environment and saying, oh, this is hazardous. So how likely are you to do hazard or apply the skills you learned in hazard mapping at your job site? Would that be just like an idea? So not very likely at all to extremely likely. So you only have 5 items. So first of all, you're already deficient there. In terms of using a random effect model.
Yeah, well, there's other items in here. There's other domains, right?
Mm-hmm.
So you can include multiple domains in some of these models. You can have multidimensional models as well.
Right.
So let's put aside.
Yeah, no, there's
the
like,
item requirement.
say 5
But
domains.
Let me just take, I'm trying to
dimensions.
think of an example might be, but let me think of a possible example.
Okay.
Let's say we have 2 types of questions. One that says, how likely are you to do blah, 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 like some hazmat that you learned in your job.
Right.
And so, ostensibly, that's an opinion or a prediction based on my personal response to this program of training.
Right.
Now let's take another one. Maybe there's situational questions. And it doesn't say, what do you think you're going to do? It says, what should Johnny do in this particular situation?
Right.
So one of the things you might hypothesize is that situational items may be more discriminating, more predictive, eventually, of their ultimate use than the other items. And one way to test that hypothesis, because if you're trying to write items that are better discriminating, you can estimate this model, and you can try to explain why items differ in their ability to discriminate among people, not just difficulty. But, there's different types of items,
right.
Or maybe it says, maybe there's questions that say, why should you not do this? Maybe that's a negatively worded question. Maybe it just turns out that negatively worded questions have a lower discrimination.
Yeah.
They don't work. And so in that case, we can only ask them 5 questions or 10 questions. We probably shouldn't use the negatively worded ones because we're wasting our time. We should just ask positive.
Right.
So, I'm not saying that there's an absolute utility in what you're doing, but the possibilities, fundamentally depends on whether you have a hypothesis or you have interest in hypotheses that are at the item level. Right? It's almost like survey design. If you're not interested in that, you're interested at the individual level. Sometimes, if you're only interested in the individual level, and you can get away with the 5 items that you have, they're good, then then don't worry about it. But if you're interested in the individual level and your items aren't doing so well, well, maybe you want to use some of these tools to unpack why or how you might develop a future version. So sometimes you're specifically interested in item hypotheses, sometimes you're not, and they're just a nuisance, but you have to deal with them. These give you the tools to kind of mount an empirical study of what they're doing and how you might improve things. It's almost like you're unpacking that black box of how individuals are interacting with items to give you more information to understand how you might improve.
Yeah.
There's other studies that were So I'm going to do a terrible job of summarizing this study because I remember it from many years ago, but it was along these lines. There's differences, at least I've heard, that there's differences in Chinese languages and some Eastern languages from Western languages in the sense that when you talk about saving money or planning for a rainy day, you don't talk about planning for, you don't speak of it as if it might happen someday. You speak about it as if when it happens. Does this sound familiar? So, I don't know the full details, and I'm going to put my foot in my mouth, but the rough idea here is that there's linguistic differences between languages, whatever they may be. And it turns out that there was a study, now ultimately it's correlational, but there was a study that was done that looked at how linguistic differences, the structural differences in languages, correlate to how people save. Now, there could be many other problems with this study. I'm not saying there's not. But it was interesting because they took up item level and they actually looked at specific words and how they were used in different languages, whether they were used with, like, it's impending or immediate, or it's going to happen. The rainy day will happen. But in English it says, oh, I'm going to save for a rainy day. And, in English, the implication is that when it happens or if it happens, it's not immediate conclusion. And so those linguistic differences were actually tested with some of these item response models, and you can actually understand the extent to which those specific features of the different languages actually correlate with, or an explanatory model, they correlate with higher savings rates or other features. And so you can take, that's a simple example of 2 languages, but now you can say, oh, well, there's thousands of other languages. We can code all the other languages along these ways to find out, does this actually generalize across other languages? And they did some of this, and they had some really interesting findings. And they're all correlational in the end, but they're really interesting. Of maybe how we talk in the language that's our kind of first language may actually influence our kind of thought patterns and how we conceptualize different things. All right, so I want to jump back to assignment 5 now. And I want to walk through it to give us some examples of what we're talking about here. I'm hoping that this is a good illustrative example and provides some of the syntax experience, some of the statistical experience or psychometric experience, and then also kind of putting it all together and how you might identify or develop item characteristics or item covariance. So we're using this workplace industrial relations survey data. We worked on this many months ago now. They were taken from a section of the 1990 Workplace Industrial Relations Survey dealing with management, worker, consultation, and firms. There's a citation there, gives you more information. The part that we're going to work with, again, this is just kind of hypothetically or conceptually a useful example. Respondents were instructed to do the following. Please consider the most recent change involving the introduction of the new plant, machinery, and equipment. Were discussions or consultations of any of the type on this card held either about the introduction of the change or about the way that it was to be implemented? So they were asked some simple questions, and they were told to say yes or no or mark yes or no. So it's a simple dichotomous model. They either endorse or agree, or they disagree. Item 1 was, were there any informal discussions with individual workers? 2, were there meetings with groups of workers? 3, discussions in established joint consultative committees? 4, discussions in specially constituted committee to consider the change? 5, discussions with the union representatives? 6, discussions with paid union officials. So the first question says, using these data, estimate a Roche model with a random person effect and fixed item using the multi-level formulation demonstrated in the LME4 package. Report the difficulties. So the model we want to run is a simple typical Roche model. Item J, person I. So we know how to do this in our typical item response format, or our MIR2 package, or the LTM package, or other packages. But let's try to actually do this in the LME4 package. So if you, on Blackboard, there's syntax to download. So first, let's take a look at these data. This is the format that it comes in. Each row represents an individual's response. Each column represents a particular item. This is what we call the multivariate wide format, and this is what we've typically been using in item response theory. Remember what, conceptually, what item response theory, what its machinery is using, or how it relates to other types of analyses. Item response theory, as well as confirmatory factor analysis, other types of things, is really just using a multivariate analysis. The outcomes are the items all happening at the same time. If you were going to do Mankova or some type of multivariate model, you would have multiple dependent variables, multiple outcomes, and then they would be predicted, or do a decomposition of the variance based on some grouping factors. So you have some variable that predicts all of those outcomes. Well, in IRT, it's the same thing, except for the outcomes are the items. So you have a multivariate representation. Your dependent variables are, in this case, the 6 items. And your predictor of interest, or your grouping factor of interest, in this case, is theta, the latent variable. Now, in our example with IRT, the outcomes are categorical in IRT, so we're not using a multivariate linear model, we're using a multivariate generalized linear model, or categorical model. And then, in addition, because theta is unobserved, we're using a generalized linear mixed model. So the generalized part, a multivariate generalized linear mixed model, there's a lot of different ways to describe these models in the literature. But let me try and unpack this one particular one. Multivariate generalized linear mixed model. That's what we're going to use to estimate this Roche model. That's the approach. So multivariate means that we have multiple outcomes in this example, and the outcomes are just item 1, 2, 3, 4, 5, 6. Generalized, we're using that generalized term because that's the kind of link function that helps you describe categorical outcomes. In other words, with a linear model, you have a continuous outcome. With a generalized linear model, you have some link function. In our case, it's the logit link, or the log odds that we have over there. Instead of saying the outcome is modeled as a function of the predictors, you say some link function or some transformation of the outcome is modeled as a linear function of the parameters. So this is just your kind of classic generalized linear model transition, going from a typical linear model to a generalized linear model. So we have multivariate generalized linear again because it's not linear in the outcome, but it's linear in the transformation, in this case the logit link. And then the mixed part in there. The mixed is the code word for fixed and random effects. That means that we have random effects, in other words, latent variables, and fixed effects. In this case, we're doing fixed effects for, in this exact example, we're doing fixed effects for the item parameters, the difficulty here, right? right now at least. We'll change that in a minute. So we have a generalized or multivariate generalized linear mixed model. It's a mouthful, but it turns out that there's 50 years of history going into this framework, into this mixed modeling, this generalized linear mixed modeling framework. So we've had this world of IRT. It's been developed. Parallel to that, there's been other disciplines that have been developing these multi-level models, and they've been running parallel for decades. And it turns out that they actually intersect considerably, and IRT can just be reconceptualized as a form of these generalized linear, nonlinear mixed models. Once we realize that intersection or that conceptual similarity, we can reformulate a lot of the stuff into other models and expand dramatically. And that's what's more or less happened in the past 10 to 15 years. So right now we have our data here is a multivariate wide. But if you remember back to last week, when we talked about multi-level models or mixed models, we need a univariate long format. And so we want to reformat this or reshape it. What we're going to do conceptually is just to take all the responses to item 1, leave them in this first column. Then we're going to take all the responses to item 2, and I'm going to take them and I'm going to stack them underneath. Then I'm going to take item response 3, all these, the whole column, and I'm going to stack it down there. So what I'll have is a long list in a single column, all the responses. Then I'll have to create a new column that identifies which item each response corresponds to. So for all the items that were item 1, I'll have a variable that says this is item 1. And then so let's say there's 1,000 people in the data set. So when I have an indicator that's not here, it says item, which item is it? A dummy indicator or just a factor with 6 levels. The first 1,000 values will say 1, 1, 1, 1, 1, 1. They'll all say 1 because they're all referring to item 1. Then if I take item 2 and stack it down below, the next one will say 2, 2, 2, 2, 2, 2, 2, 2. Go on. We'll do that for every single item. So we talked about one simple way to do that last week using this reshape library. So first I had to make sure that I remembered who was who, which responses belonged to who. And so I had to add kind of an ID to the file, and that was just which person I'm talking about. You could use anything you want, but I just use whatever row they're in. So I just call the person in the first row person 1, person in the second row person 2, and so on. That's this command. Then I use this reshape or this melt command. This is just going to do what I told you a minute ago. It's going to, so my data set now looks like this. I just added this ID called person. This next command, the melt command, is just going to say, okay, this is the ID, this is the level 2 ID or the grouping ID or the person ID. I'm going to stack each one of these, just like we talked about, and I'm going to write the person. I'm going to keep the person ID for each row. So whenever I'm talking about any of these responses, these 6 responses, it belongs to person 1. So in my new data set, I should have person 1 should show up 6 times because he or she responded to 6 items. Person 2 should also show up 6 times because he or she responded to 6 items. So now we have this univariate long version. Here is just my person ID. Here is the item that I'm talking about. And here is person 1's response to that item. So the first 6 people all responded negatively to that first item, which just corresponds to this first row. Any questions on our reshaping from multivariate wide to univariate long?
So why in reshaping it is not in the order of item 1, item 2, item 3, 4?
You can just resort that. You can resort it because they